Okay, Bismillahirrahmanirrahim. So in the last class, we have actually started the Fourier transform. Mostly we talk about both continuous time Fourier transform. And from there, we have already know that when we are taking the continuous time signal, it is called continuous time Fourier transform, converted to the frequency domain, and can be represented e to the power j omega, capital omega, or sometimes it can be represented x omega. And when we talk about discrete time Fourier transform, then our input signal is xn coming from xt with your sampling frequency, and it can be represented as x e to the power j small omega, where omega is the relative frequency, and it can be also mentioned as x small omega. In various way they have been presented. In last class, we have tried to see the algorithm in detail, and we can write it in a way. This is xn e to the power minus j omega n, and we need to go for the summation for n is equals to minus infinity plus infinity, and that is the mathematical definition of the discrete time Fourier transform. And discrete time Fourier transform, conventionally, it is known as the Fourier transform. So whenever we'll refer Fourier transform, basically we'll refer the discrete time Fourier transform. And we have done the Fourier transform for the delta function. Okay, so you have done a lot of example in your bachelor's study, so I'll not go into detail of that one. Though there could be some common portion from the bachelor's study as well, because that is the common or fundamental understanding part. If we think about different parameters, like if I want to do, let's say alpha to the power n un, or this kind of functions, okay, we can do the Fourier transform accordingly. However, there is a concept which is known as a delta function. Delta function, of course, that is in the analog domain, which refers that the integration of this delta function with respect to frequency would merge to 1. The area would be 1 for a very small duration. Let's start with 0 minus to 0 plus, which means that if we have this omega is 0, and this actually been defined as delta function. This is 0 minus and this is 0 plus. What is the area of this? This area is 1. If you narrow down this width more and more, let's say we are narrowing down, definitely the height will be increased. So that's why this delta function is known as a concept where the area is unity. The area is unity. You can there is no limit of 0 minus and the 0 plus. Okay, it actually shows that this is a very small and tiny space. Some functions, as I already mentioned, probably in some places, that like un alpha to the power n, two-sided sequence, e to the power j omega 0 n for a particular frequency, or you can also mention that cos omega 0 n, this is infinite series, sine omega 0 n, all the sequences. Basically, if we talk about all those 1, 2, 3, 4, 5 sequences, the time series n is for plus infinity to minus infinity, or in other way, minus infinity to plus infinity, they are all not summable function. They are not summable because you have infinite number for both functions, for all the functions. However, by doing some rigorous mathematical calculations, in some way, mathematicians can also find the Fourier transform of all those functions. But okay, let's say for the function e to the power j omega 0 n, the Fourier transform is this: twice pi delta omega minus omega 0 plus twice pi k, and n is equals to from sorry, k, not n, because that is a function of k. So k is equals to from minus infinity to plus infinity. Need to understand. So this is our xn. We are doing a Fourier transform and we have found this. Okay, let's say an intelligent mathematician have developed this one. We need to understand each and every part. Okay, so twice pi is a constant value, and inside the delta we have omega minus omega 0 plus twice pi k, where k equals to 0, k has need a limit. When we are at the baseband, in that case k is equals to 0. For the other terms, as we have already know that our range of vision is always from minus pi to plus pi. So this is twice pi. Then you have other higher value of the omega in the both side. So for the second lobe, the k is equals to 1. So now, whenever we are doing the Fourier transform, then we can write the general equation like this. Now, in other fashion, what we can do the inverse Fourier transform from this to this. And if we can show that the inverse Fourier transform of this function, like x omega, is equals to e to the power j omega 0, that is enough that it has the Fourier transform like this. Okay. So what we can do, we start with the left side. That means summation k is equals to from minus infinity plus infinity. Okay. And twice pi delta omega minus omega 0 plus twice pi k. And we need to do the inverse Fourier transform. So we according to the definition, this is our x omega. So inverse Fourier transform of this, we need to multiply it with e to the power j omega n, and we need to do the integration from minus pi to plus pi, because this is our baseband and we are considering this. So if you only considering this in the frequency domain, if you do the inverse Fourier transform, you can come to the time domain. You can find the value xn. So this portion shows the x omega for k is equals to 0. That is the baseband. And as from our previous experience, we know that the x omega is a periodic function. Periodic function means after pi, after twice pi, that will repeat. After twice pi, that will repeat again. So this is a 4 pi, and here this is 3 pi's. So we are only considering this baseband, and you need to put an averaging factor, and this is the inverse Fourier transform. So if we start with this and doing the inverse Fourier transform, this is the equation. And now if we elaborate the things, then what is the value of k? K is 0, so we don't care about this term. As well as this is a constant, that's why it will cancel each other. So we can write it in this way. This is from minus pi to plus pi, and we don't need to actually write. This is minus pi to plus pi. That is the limit for this value. So we have the delta. This is omega minus omega 0 and e to the power j omega n. For which value of delta, for which value of omega, this is true. Only for omega equals to omega 0, we have this delta value, because otherwise it gives 0, because the you know, from the definition of the delta function, it actually have the value on a single moment. Let's say for if I put delta n, that shows that I have the value at 0 location. If I put delta n minus 1, that means I have the value at the location of 1, positive 1. Similarly, delta omega minus omega 0, where you have the value at the location of omega 0. So no need to do the integration of that one. So we have a single value, and we can write it as e to the power j omega 0 n, because omega equals to omega 0, and for that one it got the amplitude is equals to 1, so that is 1, which gives the inverse Fourier transform, and this is our xn. So now it's easy to mention that, okay, this is our xn. We got this result. It shows that if we start with this, of course we find this in this Fourier transform as this one, and this is enough to prove that the Fourier transform of e to the power j omega n is equals to the summation k is equals to from minus infinity to plus infinity twice pi delta omega minus omega 0 plus twice pi k. Because this is a one-to-one function. What does it mean by that? If I have xn, do the Fourier transform, we have x omega. If you do inverse Fourier transform, we must get the same value back, that is xn. There is no other way. Sometimes there are some processes where you can get a different function. For example, you start with xn, you start with the function a, doing the Fourier transform, or not Fourier transform, some kind of mathematical transformation, and you got x. You do the inverse of that one, you got value b, as well as you may got the value a. So there are two ways you may go. So that is not a one-to-one function. This is called one-to-many function. So fortunately, the Fourier and inverse Fourier transform, they are one-to-one function. So this is enough to prove that the e to the power j omega n have the Fourier transform of this. This is easy from the mathematical point of view. Similarly, for un, if we want to do the Fourier transform directly, it needs some tricks. Okay, but we can do that. Okay, so let me give that example how we can do directly from the time domain to the frequency domain. As we have already know that this for the convergence, this un is not converge for n is equals to 0 to infinity. What I mean that for n is equals to 0 to infinity, if I go for the summation of un, and let's say I'm putting the absolute value modulus of that one, that is not less than infinite value. So ultimately, according to the concept of the Fourier transform, the summability is not been there, even though we found that there are some functions which do not have summability, not even square summability, but they have the Fourier transform. And these functions I have already mentioned earlier, like alpha to the power n, un, sine omega 0 n, e to the power j omega 0 n, cos omega 0 n, both are the same pattern. They are neither summable nor square summable, but they have the Fourier transform, and un is one of them. Okay. Okay, how we can solve this un? Okay, so let's take that un can be represented as is equals to xn plus yn, where we are taking xn is equals to half for all the value of n, and yn is equals to half for n is greater than equals to 0, and minus half for n is less than 0. Okay, it can be represented very easily in the time domain. What is xn? I'm just writing xn here. You'll find half all over the place up to infinity, and half there in the minus infinity. So the amplitude is half. 0, 1, 2, and up to infinity, minus 1, minus 2, up to infinity. Now about yn, if I want to draw the yn here, so how it looks like, this is yn. For the positive half, it will contain halves values. This is half, and for the negative one, it will got definitely minus half according to the formula, so that you can add those together and you get un. So you know that how un looks like. This is a step function. So of course it actually been shown that un is equals to xn plus yn, where xn is half for all the n, and yn is equals to half for n more than 0, and half minus half for less than 0. Okay. Okay. So now from our past experience, we can say that if we shift the yn in one sample, how it looks like, you can follow what I am writing here. I'm writing yn minus 1. So it will shift one sample right, and how that should be looks like half, half, half all the way, and at the 0th location it will be minus half, and now this is a minus half, and it will goes up to infinity. Now if we subtract yn to n minus 1, what will be the value? Yn point to point, so all the points will subtract each other. Only at the location of n equals to 0, you will find, this is the location 0, n equals to 0, that will be half minus minus half, that is equals to 1. At which location? At the center. So how it looks like? It looks like a delta function. If you add yn with yn minus 1, let me choose another color. If you add yn with yn minus 1, they will cancel each other. So subtraction, cancel, cancel, and this and this, they will be added, and it looks like a delta function. N equals to 0, that will be delta function. Okay. Now, what is the Fourier transform of the delta function? We can understand if we have, if you want to do the Fourier transform of 1, do the Fourier transform, we know that it is twice pi into omega. How that is so? Okay, we have the process. We can, okay, if you don't believe me, you can do the inverse Fourier transform of this function, and we can prove it. Okay, so let's do that first. Let's say we have our x omega is this. This is our x omega. We need to find the xn value. How we can find the xn? Xn is equals to average twice pi minus pi to plus pi by definition, x omega and e to the power j omega n d omega. So where half 1 divided by twice pi will remain as it is. X omega is equals to twice pi delta function and e to the power j omega n d omega. Again, this is constant. You can cross those things out. And again, since this is a delta function, it only have the value at omega equals to omega 0. So at omega equals to omega 0, what would be the value? At omega equals to 0, not omega 0. At omega equals to 0, we have that value because that is delta omega here, delta omega. So we can write it like this. It should be e to the power j omega equals to 0, 0 into n. So it actually gives the value 1. So what is 1? 1 is our xn. So we can prove that if we do the Fourier transform of 1, we should find this value. We have no doubt on that. So since this is a linear transformation from one domain to another domain, we can write that if we do the Fourier transform of half, that will give you pi into delta function. So this is simple. That is a pi into delta function. In the example, if we have the value of xn, how the xn looks like? In the case we have defined the value of xn. Xn is equals to half. Xn equals to half for all the value of n. So we can say that the Fourier transform of xn, the value is half. So x omega is equals to pi delta omega. So from this statement, we can write it straightforward because we have already proven that for 1, if we do the Fourier transform, we got this. If that is half, then this one. And what is half? In our case, that is nothing but xn. So x omega is equals to pi into del omega, the delta function. And now if we consider on y value, yn minus yn minus 1, that is again delta function in the time domain. If we do the Fourier transform of the both sides, what will be the value? Of course, this will be y omega minus, there will be e to the power minus j omega into y omega according to the law principle. And what is the Fourier transform of delta function? We have found that is 1 in the last class as well. Now from there, we can write quickly that, y omega is equals to 1 divided by 1 minus e to the power minus j omega. So this is our y omega, and we already found the x omega. So if we look back we have defined the yn is equals to xn plus yn. So we can write the Fourier transform of un is equals to x omega plus y omega, and that is previously we have found pi into del omega plus 1 divided by 1 minus e to the power minus j omega. And for this time as well, so this is the result. If we do the Fourier transform, you will get this function. It can be also written as this. Let's say that the first term is pi. I can start with the letter term first. 1 divided by 1 minus e to the power minus j omega plus pi into delta omega, and this will repeat. This omega value, this value will repeat again after twice pi k. The whole value will repeat after twice pi k. So that's why it can be written in a way, in general format. I can write in this way: the k is equals to from minus infinity to plus infinity pi delta omega plus twice pi k for all the cases, because whenever the k is equals to 0, that shows the baseband, and for the other value k is equals to 1, it reflects to twice pi. K equals to 2, it reflects 4 pi. So it actually shows the hopping where the actual value is pi. Basically the value is pi, and where the pi will be there, where is the location, and that location is shown by this kind of function. For example, if I say 5 into del n, what does it mean? It means that at the center we have the amplitude 5. If I write in this way, 5 n minus 2, it shows that at location n equals to 2 we have the value 5. But if I show in this way, the delta n plus twice pi and put a value of k, that means after this and make a summation. Summation means they are having the value. You can add those numbers together. For k is equals to minus infinity to plus infinity and putting the value constant 5. That means you have, let me draw it here. You have a sequence where k equals to 0, you have 5. For k is equals to 1, that means at twice pi, let's say you have the 5 value. At 4 pi, you have the 5 value. So that, what does it mean by this kind of expression? However, in short, I can write 1 minus e to the power minus j omega plus pi delta omega. That is enough. That is the Fourier transform of un and the repetition of the later part. Okay, so I believe I'm running out of time for the next meeting. So inshallah, we'll extend this discussion, the Fourier transform, a little bit more, and a few concepts. As I have already mentioned that about the convolution, I would like to express something graphically how we can understand the convolution, because convolution is nothing but correlation, and in DSP we are basically doing the Fourier transform. That means the convolution, correlations here and there. So how we can relate those two things graphically. So I'd like to express that in the next class, inshallah. Thank you for joining, and again, sorry for this kind of mishappening. Thank you.